Okay, I think that's the recording and the transcription starting. Yeah. Okay, so that's recording. As usual, I will upload these onto my YouTube channel. And I realise I was late with the one 2 weeks ago, but everything should be up to date now. So if you want to go back and look at any of these things, just go to the YouTube channel. And if you're not sure where the YouTube channel is, again, there is a link on Teams, which won't show up here on Firefox. It doesn't like me to embed other websites in there, but trust me, that's where it is. Okay, so as you no doubt saw, today we are following up about threads. Now, to the relief of all, this will be a shorter lecture than normal. And part of the reason for that is a lot of the stuff about threads is highly technical in terms of how we implement them. In other words, there's lots of programming stuff in there. And I've said this before, if you don't know programming, if you're not sure about programming, don't worry about it. You won't be required to know that. What it does mean, however, is that I've taken out a lot more of the stuff than I normally do. So this is quite a short lecture today. And I'm only going to cover the basics. For threads, we don't need to go into great detail. Because what we're talking about really is the idea that we started talking about last week, that a process, for some processes, it might be helpful to do more than one thing at once. That it might be helpful for a game to run a thread that looks to see whether you're using the keyboard so that you can shoot and move, and another thread to be updating the screen so that the screen can get updated. You don't want to do those one after the other, the way we were talking about before, because clearly there will be a knock-on in terms of the speed. Are we looking at the keyboard? Are we looking at the screen and jumping one to the other? So if we have a multi-core system or a multi-processor system, we can take the parts of that process where it would be helpful to run them in parallel and do so. Now, sometimes they are different threads, the keyboard thread, the display thread. Sometimes they are exactly the same thread. So if you're doing a render on a video, you might want to parcel out the data. You're running the same algorithm, but you chuck the same data to multiple threads so that it can execute in parallel and come back more quickly. So there's lots of places where we might want to do that. Games, images, network traffic, I/O, all of these things would benefit from having threads involved. But as I say, there's no real trick to it. It's simply saying, can we take some of the code, can we tease that out and make it into something that we can run at the same time? Which is why that first slide there starts talking about thread libraries. In other words, for this to happen, the operating system has to provide the services to have threads, and the programs that are written have to use those services. So it's an extension onto the APIs that we've been talking about before, which is why I was saying it's about programming as well. So don't worry if you're not sure about programming. Just trust me that if you are programming this thing, there are services available to do it and that you can work with them. So most systems these days are multi-threaded. Why? Because most modern computers these days have the ability to run multi-threaded processes. They either have multiple cores or multiple processors. So because the hardware has advanced, the operating system has advanced to support the hardware. And we see that all the time. We see, very simple level, a new printer comes out that's colour. So we put in a driver for the operating system to support a colour printer. That's a very basic thing about the operating system evolving to take note of new hardware. I've got a trackball rather than a mouse, and it's wireless. So I had to install a driver both for the Bluetooth connection and because it's a trackball rather than a mouse. And it's got a scroll wheel, which basic mice don't have. I know most of them do now, but didn't used to have. So that's an extra part of the operating system that had to be added in. So it's not unusual for operating systems to add in extra stuff to support hardware, and that's all this is. It's the operating system saying, well, maybe we want to update the display more quickly, or go and get some data, or do some background spell checking. Have you ever wondered why Word can immediately put the wee blue wavy lines or the red wavy lines as you're doing it? It's because it runs a spell check thread or a grammar thread in the background and can then say, oh, you've got a problem here, which then feeds into the display thread to update your Word document. Why don't we run multiple processes for this? The idea is if we run a thread, it's less resource heavy. In other words, we can use a lot of the same things, and you'll see that later. So we're not having to load in a whole new process with all the overhead that we saw last week. We can simply add in some extra code, share the code base, share the memory, share the data, and that makes it a lot quicker to run. Now, most threads run as a kind of client-server approach. So the kernel supports multiple threads. The client requests a new thread at the server. The thread's created, and then it can go back to listening for new ones. So the client here is a process, the server is a kernel. Not always, but just for the sake of this discussion. And the kernel will then create a new thread. As I say, that's really quick. Sometimes you can get processes that stop, either because they were meant to, like this PowerPoint presentation that stopped because I haven't pressed a button. But you can also get processes that stop because of other reasons, and that can stop anything else happening. So if you have a multi-threaded process, you can continue to have the response. Just because something's happening in the background, an Excel spreadsheet's been calculated, doesn't mean you shouldn't be able to update the system so that you can see that it hasn't crashed. The other thing that threads can do is share the resources. So like I said about the Word spell check, the data itself is shared. It's shared for the editor, it's shared for the display, it's shared for the spell check. It's all the same data. We don't have to load all that in as a new process and have all that overhead. We just share that same stuff. And as we also saw last week, if we had another process and wanted to share that data, we would have to pass it as a message. And that would also have overhead. So this way we can share all the stuff that we already have in there. So it's much cheaper in terms of process time, in terms of CPU time, in terms of, well, any metric that you want to use for your computer. It's much cheaper to go to a new thread than go to a new process. And the last thing, of course, is if you're using threads, as your hardware increases, your process can become more efficient because it can take advantage of all these new things you've added, all these new multi-cores or all these new multi-processors. Now, it's not easy, and this is what I was saying earlier about programming. There are challenges when you program using threads. They're on there, they're in big bold letters. If you understand what they are, great, that's the challenges. If you don't understand what they are, don't worry about it. Just remember that there are challenges for programmers who are having to implement these threads. So there's a couple of ways that we can do this. We can either run things in parallel, so the system runs more than one thing at once, or we can have concurrency. And that's what we were talking about last week for things like a timeshare system. We have multiple tasks, but each of them has to go at its own speed. So lots of tasks making progress, but only one thing can make that progress. With parallel tasks, however, we can do lots more. And there's two ways that we can do this. We can either split up the data. So I said earlier about rendering an image. We can split up that image and send chunks to multiple tasks to do that rendering. Wait for that to come back and then merge it all together again. So that's data parallelism. And I don't need to remind you about the text in blue. These are things you probably want to remember. So there's data parallelism where we split up the data, send it out, get it back. Or there's task parallelism, where we actually do different tasks, the editing, the spell checking, the displaying, whatever it might be. We do all those tasks at the same time. All of this is supported by the CPU, so we need hardware in place for that, and that hardware gets more sophisticated as we move on. That's talking about an Oracle Spark T4. I meant to look up when that was first brought out, but it was a while ago. And processors, not surprisingly, are getting more and more sophisticated with more and more cores and more threads available. In other words, the hardware is getting cheaper, so our machines are getting faster by making use of this. So there's just a simple diagram for the difference. 2011, thanks Ryan, over 10 years old. But the point stands. These are examples of processors that allow that, and as you can imagine, things are getting faster every year. So concurrent execution, that's what we were talking about last week. T1 takes some time, then T2, then T3, then T4, then you're back to task 1, task 2. With multi-core systems, you can split that up. T1 and T2 can go together. T3 and T4 can go together. If you have more cores, you can split them up more. If you have tasks that are more processor dependent, more CPU dependent, you can decide actually that you want to devote more time to them. So here we've just split up T1, T2, T3, T4. We could, though, decide that some tasks are more important than others and assign them to a specific core. So rather than just splitting them up 1, 2, 3, 4 in order, we could say, no, we're actually going to dedicate core 2 to task 1 because that's the one we want to keep updated, maybe a fast moving display, and have all the other tasks on the other core. We have the choice is the point. We're not, it's up to the programmer to decide how they want this to happen. Now, as I said, it is more tricky to do. So here's a single process. And this is what we talked about in previous weeks. We've got the code, we've got the data, we don't have any files that it's accessing within the CPU. And again, remember, same kind of idea as the little man computer, where we have a program counter, instruction register, address register, accumulator. Clearly, more sophisticated CPUs will have more than just that, but it's exactly the same concept. Those are the registers. Other CPUs will have more registers. We'll have a stack where we can store data as well. Where we have multi-threaded processes, we can make use of the same code, data, and files, but we can add in the hardware support to have multiple registers and multiple stacks. So you remember last week we were talking about swapping over registers when we swap processes to get to where we were in the process. If we can keep multiple threads running with multiple sets of registers, multiple stacks, it means that all of these things can run together. But of course, that takes hardware support, and hardware support costs money, which is why some CPUs cost more than others. Are we okay with that so far?
Yes. So a thread is just a process, basically.
A thread is very specifically not a process, because a process has code, data, and files. But a thread is a part of a process where it can run multiple pieces of code, if you like, at the same time, but it depends on which ones you've chosen to split up. So as I say, when you're running Word, you might have chosen to run the spell checker as one thread, so you can check as you're going along. So it's not a different process, it's a part of the original process. Okay, and it's a very clear distinction there. Threads are faster, threads are more lightweight because they're not new processes. You don't have that overhead. Is that okay? Yep.
Yeah, thanks.
So in these diagrams, these are both processes. These boxes are both processes. It's just that this process can do more than one thing at once. And the more than one thing at once is the thread. Single processes that we've been thinking about before still have threads, but there's only ever one and can only be one. All right, so given that we have that, presumably we can start thinking about how we can go faster. And in theory, you would think that if we can afford the hardware, if we can just chuck more hardware at a problem, in essence, we can make a system go as fast as we want. We can make the execution go as fast as we want. And yes and no. Because there are some things that we can split up and we can run in parallel, but there are some things that have to run sequentially. So there is actually an algorithm for it. And again, as with the programming, if you're not keen on maths and equations, I'm not going to ask you to memorize this. You can just take my word for it. And the important bit is the S. S is the serial portion, things that you have to do one after the other. Nothing can happen until they're done. You know, you can't start rendering a file until you load it. Loading the file is a serial process. It just has to come in. There's nothing you can do. So you can't speed that bit up. Once it's in, you can then render it, and then you can save it, and it goes back to being a serial process. So you can't just always speed it up as much as you would want. The serial portion is a huge drag on it. So we can actually work out, depending on applications, a mix of parallel and serial parts, how much faster we can go. So there's an example there. If the application can be 75% serial, 75% parallel and 25% serial, doubling the cores from 1 to 2 doesn't double the speed. It's 1.6 times faster. So we can get faster by adding more cores, but it's not just as simple as extra core is an extra percentage of the core. But we do know what it is. Okay, so how do operating systems cope with this? What do they do? And again, this is part of the thing where you're probably going to feel that I'm jumping over bits. I'm not going into great detail, and I'm not, because there's a combination of the stuff that I want to do so that you understand it to a certain level, and the bits where you would have to understand it to go away and program it and make it work. So I will do it to the first level, not the second level. But if you want to know more, of course, it's all in the book. So I said this is about programming, and I've said this is about programmers understanding how threads work and using the appropriate libraries to make that happen. And there are multiple libraries to do that. POSIX, so the Unix-based ones like Linux, have a thread library, as does Windows, as does Java. They all approach it in slightly different ways. Now, those are the user threads. So that's something where the programmer has said, I want this to be a thread. However, the kernel then has to support those. The operating system has to support it as part of the kernel. So you have to map the threads that you've created onto the kernel threads. And remember, there'll be a few glitches in that. You might want to create more threads than the operating system or the hardware can support. You might have multiple processes running, which can create multiple threads and may or may not keep running. So it gets to be very complicated. So we've got lots of different models, depending on what we have. So here we've got lots of user threads. So the programmer said, yeah, give me lots of these. These then go to a single kernel thread. Now there's a problem with that straight away. If any one of these things goes wrong, it blocks all of them. And we don't really have parallelism. If we've only got one kernel thread, they're not running at the same time. So it's not well used, as you can imagine. Far more frequently used is each user thread. So each one that the program has said, yep, let's make that a thread. That maps to a single kernel thread that the operating system makes available. Each of those can then run in parallel and you get that speed up that we're looking for. But as with any resource on the operating system, it might be restricted at some point. So in the same way as in the process section that we looked at last week, when we're doing timeshare, we might only give a certain amount of processor time to each process. We might do the same with threads and say, no, well, hello, process number 1, you've already got 4 threads, you're not getting any more because process 2 needs them and so does process 3 and so on. So there might be restrictions. However, this is a common model, and you can see there, Windows and Linux both use this model. So here there's a one-to-one. You know which user's thread is going to which kernel thread. Some systems do a many-to-many. So there are still lots of user threads, still lots of kernel threads, but they are managed by the operating system to create the amount of kernel threads that you need. So again, this becomes more complicated. Again, it takes more resources, and again, it takes more skill when you're programming, which is why Windows has a whole other library to support this, something called the Thread Fiber package. So it can give you more, but it's more complicated to write for. And this is a bit where I was saying right at the start, I'm going to jump over bits, because if you're not into programming, you're just sitting there going, what? So at the moment, just trust me that there's many-to-one, one-to-one, many-to-many, and a two-level model. And a two-level model just takes the many-to-many model, throws in the one-to-one model, and says, okay, well, you can have many-to-many and let the operating system look after it. But if you've got threads that you really want to be looked after, you can assign them to be a single kernel thread. And the technical term is binding it to the thread. So again, it gives you all of these options, and they're not easy to use. If you're programming with threads, it gets tricky. And the libraries that are set up to do this aren't always easy to follow. Apart from anything else, it has to understand the two different sets of threads, the user threads and the kernel threads, and how they work together. So there's different libraries supported, set up to support these things. One is pthreads, and they are quite common for Linux. And if you've forgotten what I said a couple of weeks ago, Mac OS is a version of Unix, as is Linux. So the Mac supports that as well. The point is, it's a standard. So this is how it says they should work, not how they actually work. What's the difference? Well, the standard for a car is that it has a steering wheel. The implementation is, does the steering wheel go on the left or on the right? So they can be two different things. So let's give you some quick examples of how Windows and Linux cope with that. There is an API in Windows, and as I said earlier, it's one-to-one mapping. So one user thread to one kernel thread. So one that the programmer sets up, mapping to one that the operating system looks after. And there needs to be, as there is with processors, some identification. So like with the processor, the thread has an ID and it has a set of registers and it has a stack and it has all that kind of stuff that it needs to actually run. The fancy name for that, blue text alert, is the thread context. So what is the state of the thread right now? That's then set up so that we have a control system that starts with an executive thread block. That points to where the kernel thread is, and then has a thread that actually runs from that. In other words, something like this. You have the executive thread here. So which thread is it? Where does it start in terms of the code? Which process started this thread? And all that, any other information that the operating system deems necessary. That executive thread points to the kernel thread, and that has to keep all the scheduling information, all the synchronization information, the data in the stack, all that kind of stuff. And that then points to a specific thread. And you see that we've split this up. So this is how the operating system looks after it. So this is in the kernel space. That then points to the user space, the actual code that the user wants to run. Linux does something similar, but it doesn't call them threads, it calls them tasks, and it uses a clone call. And that's the bit that allows it to share all this stuff that we saw way back at the start. Clone says, keep using the same code, the same data, the same files, but give me a new set of registers and a new stack. And Linux gives you the option of which of those you want to share. Do you want the file system? Do you want the memory space? Do you want the signal handles? You've got a message in from the keyboard or from the network or whatever. Do you want your files shared? So it gives you that more detailed control that you can use. And that, you'll be pleased to know, is that. I told you it was going to be a quick one today. I told you we weren't going to go into detail. In part because there's no easy ramp up with threads as far as I'm concerned. So I've given you the idea of them. To actually use them, you sort of get a wee bit of knowledge, and then you have to get an awful lot of knowledge. And there's no kind of nice wee going up knowledge. So what I've done is given you the basics of it that we are going to need for our assessment, but not the lot of knowledge that you're going to need if you're going to program them. So any questions about that?
I know it was mentioned in the previous weeks, but could you remind me what a system call is, please?
Okay, a system call is where the, where the user process and the operating system processes interact. So I am running a PowerPoint. I have a mouse, as you know. If I want to click here, PowerPoint doesn't do the clicking. The operating system does the clicking. So a system call is anything that the operating system looks after. Changing the display, getting information from the mouse with the click, getting files. It's anything that you want to provide as a service. So you don't want PowerPoint to have to rewrite getting files from a hard disk or a USB or a network drive. You want the system to have that. And then you run a system call to say, get the file. The file is called fred.txt and it's on network share Barney. Go do it and don't bother me with the details. Just run that system call to get that. The operating system then does that, goes to get the file, takes care of all the nitty-gritty of it, and sends it back. So the system calls are all the things that the operating system looks after for the system. Displays, I/O, file systems, all that kind of stuff. Is that okay?
Yeah, that's great, thanks.
Any other questions just now? Yeah. All good is what I'm seeing in the comments. Okay. If there are no more questions, let me stop recording.